Bien, y les decía que vamos a pasar de la música al espacio.
As I was saying, we are going to go from music to space right away with Miguel San Martin, who is going to tell us about his trip from Viking to Curiosity and the challenges of descending in Mars and what it's like to work with NASA. Welcome, Miguel. Can you hear me? Yes. Firstly, I would like to thank Genexus for having brought me here and giving me the opportunity to tell you about the work that we do in NASA in Mars exploration. And I always like to start my talk by saying why we explore Mars. Mars is one of the scientific objectives of NASA, but it would seem that for some reason we invest more money and attention in Mars. The reason is that scientists believe that at some point Mars was a warm planet that may have had life. It was similar to the Earth, and here we can see a river with a basin. And this would seem like the rivers that end in the river plate if everything dried up. So life needs water, and it would seem that 3,500 millions of years Mars had a lot of water, and maybe the right conditions were there for life to surge. And why are we interested in knowing whether there was life in Mars or not? Because we only know about life in planet Earth. Right now, we are only 100% sure of life on planet Earth. Therefore, if in our own solar system we can discover that life is not purely terrestrial and that there is life in Mars, then we could dare say that life is not a cosmic accident, that life happens elsewhere in the universe. Why do we want to know that? Well, because we want to know whether we are alone in the universe or not, which is maybe the most important question the humanity can ask from a philosophical point of view. This is a drawing that represents the possible oceans in Mars, and this is probably where the water was concentrated. Now, the first mission that went to Mars to test this hypothesis was called Viking. I was living in Argentina at the time, and it was a mission, however, that inspired me a lot. From the point of view of robotics, the cost was not the same, but the dimension was similar to the Apollo project that put men on the moon. Now it would cost more than $6 billion. It was necessary to invent everything: the computers, the motors, the radars, and the parachutes that we use even today. And what characterized this mission was that it had equipment to detect life directly, looking for metabolic processes and photosynthesis, looking whether there were any creatures that could breathe or that generated gases or that lived from plants, not very different from us. The vehicle was a great success. It arrived in Mars, and I was young. I followed it from my place in Rio Negro through the BBC, and the next day I went to the village and saw this photo and saw the print of Viking's leg, of one of its legs on Mars surface, and I decided that this is what I wanted to do. I wanted to study engineering and work on this kind of thing. And from the point of view of engineering, it was the ultimate technical challenge. So this is what took me to the US. People who are experts in arriving on another planet, and there are not many, found this rock which they named Big Joe. And in spite of the best intentions of landing in a flat place without rocks, analyzing the photos they took,
they were taking the photographs from the mothership where the vehicle came out. Well, they landed in a place where if they had landed some meters to the right, the vehicle would have hit the rock and would have been a total failure. So that's in the mind of the engineering. We made it. That's what we say, we engineers. And in the future, we have to do something different from this, because this system has large limitations. But anyway, we were there. I was in Argentina. The research went on, and one of the instruments called labeled release showed a positive result. People from the Viking told us, the curve showing that there was life. Now, unfortunately, there were other scientific instruments giving a negative result. Even the instruments looking for organic matter, organic compounds on which life on Earth is based. And so perhaps the scientists from Viking thought that a bit arrogantly that if there was life, it was going to be life like ours. But that was what they knew how to look for. So they could explain that a positive result was false, and that the chemistry from Mars soil was quite complex, showing that type of life, which wasn't the case. In brackets, the scientist that designed this experiment is someone from MIT, thinks that the result was positive and that there was life, but the scientific community doesn't agree with him in general. Well, anyway, what's happened is that the possibility of life had been so much anticipated that a colleague of mine who was part of Viking and who's also working with us, and that's was a very good friend of Carl Sagan, and he was so convinced that they were going to find life that Sagan tried to put a lamp to take a photograph of the animals coming out at night. When they didn't find any organic compounds, any microbes, unfortunately, they were so depressed that the Mars exploration program was killed. It was killed for 15 years. It was a great disappointment. Those were the exact years that took me to finish high school, get to the US, study English, get to the university, and enter the JPL. But I never thought that the next mission to Mars, when I saw that first photograph of Viking on Mars' surface, that I was going to form part of that mission. But this one was going to be a very different mission. And now scientists, are a bit more intelligent, and they said, we're not going to promise that much. So instead of looking for life directly, we're going to look for the necessary conditions for life. And the first thing is that to prove that water evidence is true, that there really has been water on Mars' surface, and that strategy was called follow the water. The following missions had this follow the water thing. When we're talking about water, it's water that must be liquid and stable, good for life, forming rivers and streams with the right pH, not too acid or not too salty. And in spite of the fact that there are many organisms living in extreme conditions, anyway, scientists wanted to look for a more neutral type of water. And so that's what the purpose of this mission. And we also wanted to develop a new landing system. Why? Well, because what happened was that we had two problems. The first one was that we had to solve the problem of Big Joe, the one that almost killed the Viking. And the other one was that we had a much lower budget than Viking. It was less than $250 million. And Viking had used $6 billion at that time. So the idea was to find something much easier. So the first thing that we thought was, what are the things that are costly? Well, the costly things for space is computers, software, radars, gyroscopes, navigation systems. So this group of engineers, they were all mechanical engineers, they thought of doing something very mechanical, an air bag that could bounce. We were total enemies because we were pushing the price up in these missions. And even at the beginning, well, here you see the sequence of landing, which wasn't that easy, in fact, but the speed of the parachute was much higher than what the airbags could resist. So, well, they had to admit that they needed a radar and software. So bring in Miguel and his people to do the job, so that they could stop the vehicle in the very last second. And that required a certain algorithm that was quite delicate. As the legend goes, the head of the project was so mechanical, he didn't want any software. He wanted a sort of a mechanical temporizer like the old washing machines in the 50s. But then very quickly we persuaded him that we needed some software and a computer and rocket engines. So, but suddenly we realized it wasn't that easy, and it wasn't less easier than what we thought. This is a photograph of the Pathfinder. You see the Sojourner rover. There is a spaceship that is absolutely independent. That's the mothership with its own computers, and it manages the software for the trip to Mars and landing, and also operations on the surface. And then the vehicle is absolutely autonomous and comes out. Landing was very successful. This was one of the first photographs, beautiful photographs with Sojourn. Well, you can see the airbags. Once the vehicle lands, you have to retract them so that they are not mixed up with the wheels. And so there are some petals that open up. And in that way, the vehicle has the pedals down and the vehicle is up. And it worked until the first time we tried it out. Now, here we can see a photograph of the Sojourner exploring a rock. Now, some of the things that we learned, that what was quite obvious, that while the Viking, well, scientists were very frustrated because they were analyzing the rocks around it, but they wanted to analyze the rock that was on the other side, and of course they didn't have enough space. So we said we had to solve that as well. So we need a mobile explorer. And that was the first experience for the U.S. The Russians had already done it on the moon. And so scientists said from now onwards, we want rovers. This is another photograph that's very nice. This is one of my favorite photographs at that time because it was a rover photograph taken by rover to the spaceship. Well, as you can see, this system, although it's passive and with airbags, it has its complexities. They complain about software and computers and control complexities, but this has its disadvantages as well. And I always reminded them of that to them, because sometimes we didn't do it very well. Well, the Pathfinder saved the life of Matt Damon, in The Martian. I don't know if you've seen the film. I'm trying the way of using the North, and we laughed our heads off because most certainly he discussed it with one of my colleagues to see how he could find the North. Well, this was a mission of engineering to land something and to learn a more economical system, and the question of water. And then we had these two other missions that were hired. It was JPL. It was private industry. One was the Mars Climate Orbiter, and the other one was Mars Polar Lander that were going to land on Mars. And this was going to be the new mantra of NASA. And they were going to be done with a very low budget, showing that they could do things in a cheaper way and get to the same point with a little bit more risk. Well, unfortunately, they both failed. In the case of the lander, as I was telling the guys from Genexus, it was one single code line that has taken 10 seconds to write to reinitialize a state barrier and write false. But I always tell young guys that in all these topics, 99.9% of doing everything right is not worth it if they have 0.1% that is bad or incorrect, because that could mean this tragedy. And so now what NASA is thinking about the next mission. There was a twin mission. So NASA said, let's take that to the museum. Let's have the same landing system that was successful last time. And that's how we had this Mars exploration rovers, which meant the Spirit Opportunity mission. It had the same landing system, but instead of having a mothership and a rowboat that was separated, what we did was to put wheels on the mothership, and we had only one vehicle that was hiding. You could see all packed up in that pyramid, tetrahedron that is protected while bouncing. And that was the idea, and we said that has worked. Now we don't have room for failure, because NASA was coming from was being quite ashamed having failed in 2 missions in a very short time. So this had to work out. Now the trouble was that very shortly after making the test, this system was very heavy, and we suddenly realized that you'll see this was one of the tests of our airbags. So that kind of thing would happen, those holes there. The same thing had happened with the Pathfinder, but since the size and the weight of the vehicle were much higher, we came across all kinds of problems, and we could see that this is a very difficult system to model. It's practically chaotic, the way that fabric interacts with the rocks. And the only way to improve the system is empirically. And so we said, let's put some more fabric, or let's, instead of doing cross-stitch, let's change the stitch, and, things that we don't want to do, because we want the certainty that this works. And something that's so experimental is not something that we like. But, well, we were up to our ears in this, and we had to make it work. But once again, we can see what the problem is when you want to do things passively without control. And so you would move the challenge from one place to the other. You weren't solving anything. You were creating a new one, in fact, because this is a system that couldn't be modeled. And even at the time of despair, to try and understand, we put a plastic rock in it with pieces of rock to see how the fabric was interacting with the airbag. and we didn't learn anything from there, only that it was going to be, it was a very big problem. We didn't know how to solve it. So, well, mechanical engineers went on putting in layers of fabric, and we put in more complexity. And I don't have time to tell you about all the details. I can do it outside, but we had to add computer vision at a time where everyone wanted to do mechanical, and now we have computer vision suddenly to be able to compute the speed of the vehicle and turn on some new engines to reduce the speed, the horizontal speed of landing, so that the wheels don't break down. So we ended up by having a hybrid system. It was mechanical, it was passive, but on top of that, we had to put all the intelligence of computers, algorithms, and even computer vision.
So this complex machine can be seen on this video. Actually, what we see here is an animation of the telemetry of the landing of the Spirit. So what you see here is what happened that day.
Al principio acá ya está el paracaídas.
Here we see the parachute already open and the system has been deployed. The rover is down there. And the radar is here making the calculations about the height and the speed in order to put the airbags at the right moment and cut the cord so that the vehicle is freed and can bounce. And this had to be done with a precision of less of 1/10 of a second. And the engine start, and you can see the height regarding the soil or and you see how it bounces here. We received the telemetry after the landing. We couldn't have a direct link to the Earth, so what we did was to modulate the tone of the radio frequency in order to send some smoke signal saying that the vehicle was functioning and the parachute had opened, but the level was very low. And here you see how it bounces and continues bouncing. But it was a success. It in both cases, both missions went well, and we see here a photo like this one in particular. And it says opportunity in Aguila Crater. You see the construct and you see the bouncing of the airbags, which have ended up in a crater. And one of the interesting things, or another one, is, well, this is a carcass that protected the vehicle. And another interesting thing I was saying is that the geological material had to be investigated by a geologist in order to determine whether there had been water there. And not only had it functioned, we had already discovered something that had a lot of scientific value. But then came curiosity, and as you see, we are talking about a vehicle that weighs almost 1 ton and has the size of a Mini Cooper. When we showed this picture before the landing, the people from BMW, that are the owners of the Mini Cooper, sent us lawyers to tell us to stop showing this photo and making comparisons. And here we have the whole family of robotic vehicles, so that you see the leap between them. Curiosity required a bigger vehicle, and we really don't know how we are going to make it. And it was also necessary to reduce the size of the landing ellipse to a size that could be better determined. This is the place where the Curiosity was to land, and the mountain has less than 5 kilometers in height. It's very interesting because the mountain was also built by sedimentary layers that contain the geological material of Mars. So you can read it from inside out. The oldest most ancient layers are at the bottom and the most recent ones at the top. So we could find at the bottom where the right living conditions existed. In order to land there, we had to reduce the size of our ellipse, and I'll tell you how we did that. I always said that it was landing between a rock and a hard place, because we had the mountain and the crater and the edges of the crater, and all of them were very dangerous. So if we did not fall in this area in particular, we wouldn't be successful. So these were the 7 terrifying minutes, the 7 minutes of terror, and the stages were the same. The vehicle's entry, you see it here, it arrives to Mars at on the highest to the highest layers of the atmosphere, and in 7 minutes it has to land safe and sound. And it takes 3 stages. Firstly, the entry in the atmosphere, when the vehicle brakes, when it gets in touch with the atmosphere and the friction of the atmosphere, the kinetic speed of the vehicle becomes heat energy. Therefore, it has to be protected by a thermal layer. Then, when it reaches 10 kilometers, it opens a supersonic parachute, which reduces the speed from 1,500 kilometers per hour to 10 kilometers per hour. The atmosphere helps to decrease the speed, but it's less dense than the atmosphere of the Earth, and therefore the vehicle is still falling with a parachute at 300 kilometers per hour. So it needs to brake once again, and that is why it has engines to stop it. So this is the first stage. We have here the capsule I told you about, that protects the vehicle when it enters the atmosphere, and again comparison with the Mini Cooper. Once we landed successfully, we were still showing the pictures, and BMW was not complaining anymore. You can imagine why. And this is the thermal shield that protects the vehicle from high temperatures. In order to reduce the size of the landing ellipse, we had a guided entry for the first time. In the past, the entries were ballistic, but now Curiosity had a guided entry, which was the same that the Apollo used to arrive in the ocean near the ships that were going to pick up the crews. The engineers of Apollo died, unfortunately, during the Curiosity process. The displaced vehicle has to be put at the center so that the capsule comes at a certain angle, and there is a vector that can be regulated afterwards with the engines of the rockets, and the vehicle is guided like if it were a plane. All this is done automatically. The 7 minutes of terror, due to the fact that everything is automated and there's nothing you can do from the Earth. And the first time we tested it, it was in Mars, so we couldn't do anything unless through a simulation. So the tiniest error that we called unknown could spoil everything, and that is what would keep us awake at night. You can see here the various landing ellipses compared with the crater, how they were reduced, and the size of Curiosity, and the only one that could get to this place was Curiosity because it had a guided entry, and you can see how close it was from the center of our target. So it was the first time in which we used this technology. The following stage is a parachute, which is supersonic, one of the world largest, 50 meters long, 25 meters in diameter, and we have a love-hate relationship with the parachute. We love it because it helps us a lot to brake, and it helps us in size and volume, and we hate it also because sometimes it does not open or it breaks, as you see in this test, a structural test of the parachute that we carried out in Ames Research Center. It did not work, and this is one of the parts of the 7 minutes of terror that we fear most because it's very empirical and difficult to model. This is a parachute that opens successfully. And you can see in slow motion the complexity of the moment in which the parachute opens. The conditions are not the same as in Mars, and it's impossible to model, and we hate everything that cannot be modeled. So we are at the mercy of what happens later. And then the third stage, it's necessary to make the vehicle land in some way. We used these airbags in the past, but we need the engines of the rockets, and we looked for ways of putting airbags, but imagine a vehicle of more than 1 ton bouncing again and again in Mars. We could put radars or anything because we had the money this time, but if you land a vehicle and stay short by 1 meter, well, that meter is very complicated. It's not easy to lift a car that is 1 meter high. You need ramps, but there's no place in the capsule for metal ramps, so we need something inflatable. And it tried everything until we had this idea of using something similar to a helicopter. And this is the final result in this artistic illustration and then in this simulation. All the physical aspects are well modeled, and we had a control system. And one of the novelties in this system was that the crane, the sky crane, keeps the vehicle until it has been completely deposited on the surface, until touchdown, and we could land on slopes and also if there were Big Joe rocks. So it was a high vehicle which thus became much more robust than in the case of Viking. These are the tests we made so as to make sure that the mechanical part of the sky crane would work. But we never turned on the engines. The sky crane was tested for the first time in Mars. The landing is very benign. It's slow and nothing is broken. So it was quite simple. That was our motto. Let us land slowly, and even on Big Joe, provided the rock is not so high that it hits the belly of the vehicle. It required a very precise radar that we developed in the lab, and we had a lot of software and expensive computers, but we had designed a system that could be modeled, unlike the airbags. The radar required many tests and helicopters, as well as aircraft to reach supersonic speeds. All this was extremely expensive, but finally it allowed us to land a 1-ton vehicle. These are quick photos of different parts of the vehicle. the Curiosity so that you can see the size compared to a person. This is the arm with the scientific instruments. I could do another presentation on this arm, and it has nuclear energy. It has a plutonium battery. It's not solar. More photos. That's me taking a nap. And now I'm going to show you a video so that you see how Curiosity landed on August 5, 2012. This is the camera and the photos it took during the descent.
El vehículo en este momento se encuentra bajo el paracaídas.
The vehicle is oscillating under the parachute, and I'll tell you the exact moment when it is freed and starts its flight under propulsion.
Ahí se desprendió el paracaídas, el vehículo está...
There it has freed itself from the parachute. It makes an evasive maneuver so that the parachute does not fall on top of the vehicle. That would be a very bad day in Mars. And now it's in vertical direction and it starts raising dust. You are going to see the wheels right before touchdown. That's the wheel. And this is the photo of the Curiosity. We see here Mount Chart and the wheels on Mars and the shadow of Curiosity on this Martian landscape. We fill Mars with waste, but fortunately the Curiosity landed safely and successfully. And then we took photos from one of the vessels that was in orbit. We made it take photos and when right at the moment of touchdown, and we can see the details of the parachute. This was the first movement of the vehicle outside of the landing place. This is a photo taken by the camera of the robotic arm, and you can see there the mount. This was the first selfie in Mars. And very quickly it started taking pictures. These geological structures are made with layers, as you can see. So geologists, my friends who explain things to me, have said that it is very clear that in all likelihood water had to do with the formation of these rocks, acted in the formation of this rock. And this is the bed, the dry bed of a river on Earth and in Mars. So it could be in Mars too, the dry bed of a river. The rocks are rounded due to the friction of the water. This is the famous Mount Sharp. And we can also see the sedimentary layers. The robotic vehicle is going up the slope to study those layers. And I will leave you now with a video to show you how the landing was observed and celebrated in various places in the US.
Things are looking good. Coming up high. Vehicle reports entry interface. At this time, begin pressurizing propulsion system to increase the thrust of the system. Use that for all maneuvering atmosphere for altitude.
Bueno, esos fueron el resultado de 8.
So this was the result of teamwork. Thank you very much. These stories are very, very fascinating. And one of the questions was, this was just one shot. How long did it take you to work for this one shot? No matter how many adjustments you do, there are so many uncertainties. Yes, it was $2.5 billion and 8 years. 2.5 billion. Yes, we were a bit concerned. And I imagine that there has to be a lot of pressure behind it, right? Yes, there is pressure, but our bosses from the NASA, from Washington, had told us that these things are difficult, that it might not work. We had already showed that we had worked very hard, and that if it did not work, we were going to get up and clean the dust of our clothes and then try again. So they had taken out that huge fear of spoiling the party. And the worst thing is if something bad happens and you had something to do with it. Yes, without any doubt, after so much work and such huge figures. We were saying that you had to decide if a few days before touchdown, when the vehicle was already in space, you received a mistake, or what? Could you decide something at that moment? No, once the vehicle had left, there was no way of delaying the moment of touchdown. The laws of orbital mechanics establish that you are going to arrive on X day, and we left without the landing software. We had a beta version, and 2 months before landing, we sent it because we were told, well, no more changes in the software, and that was 2 months before landing. It was a Wednesday, but on Sunday I discovered with my team that there was an error in a parameter in the software. So what happened when you realize that? When you say, hey, listen, there's something I have to tell you. It's not for anyone. Your blood pressure has to be very stable. Yes, and one of the things I'm more proud about working in HPPM, and it's the reason why we are so successful, I think, is that there is a culture of communication, teamwork. Yes, I didn't hesitate for a second to go to the chief of the project and say, Peter, we've got a problem. In my area, there is an error in the software, and we didn't fear retaliations. There would be retaliation if I had hidden the error. So that type of communication is rewarded. But the choices were not to do anything, because we had to prove that the error could have very bad consequences. But if the consequences would not be so serious, well, doing the change and sending a command to the vessel and changing that parameter so close to landing were also risky. There might be an error in the software that could have worse consequences. So the tension was to prove that maybe we had to do it or not. So you told your boss, you decide or what? Well, it's a long story. I could make another 1-hour presentation. Did he ask you what would you do? Well, yeah, it was a long conversation. Finally, he divided the team in two. One part of the team, myself included, were told to analyze the consequences if we did not change the parameter. And we spent the whole night from Friday to Saturday studying the possible consequences and making simulations. And then the software team had to change the parameter and model the software and the hardware and analyze what would be the danger of changing the parameter. And then the next morning we all met, and the chief of the project said, this is the most difficult decision in my life, and I was not very happy about that. But we voted, and most of them, since we could not prove that not changing anything would lead to failure, well, I told Peter, we have not slept much. Maybe we have not done the right thing, but what I know is that during the last 4 or 5 years we have flown the vehicle in the simulation in one way, and this is a different one. So did you reach a consensus? No, the consensus was not to change the parameter, and the chief decided to change it. But the interesting thing is that he said, although most of you have said don't change it because there doesn't seem to be a problem, I decide, and that's why he said it's the most difficult decision in my life, I decide to change the parameter. And immediately we went to tell the managers in Washington, the managers of NASA, about to tell them what we were going to do. And then he congratulated me. He said, good job, and he sent me to sleep. And I said, well, but I made a mistake. And he said, but you came and told me that you had made a mistake, and this is what we should expect. Very good teaching. And someone else said, why did you decide to change the parameter when all of the experts were telling you that it was not necessary? And the answer shows why he was the head of the project. It is $2.5 billion, him, not me. He said, because I wanted the team to stop thinking of the problem and to start thinking of the next problem. If I had not done it, I know that Miguel and his team would have continued getting distracted by this issue. But so we had to get it off the table because we had to land in Mars the next day. So it was not so much a technical decision, but a human one. He needed the team to stop worrying about this matter that had already taken too much time. So finally, when it worked, phew, let's not do it again. I'm not going to ask how you celebrated that day. Yes, it was real fun. How many people work with you in the team? Well, the maximum for curiosity inside our team was 800 or 1,000 people. Not 800,000, 800 to 1,000. But we also bought many parts from other companies. For example, the thermal shield was made by one company, and so was a parachute made by another one. At the end, we were 200, 300 people. And finally, and what keeps you awake now? I am working not on a project, it's a study, trying to convince NASA and scientists to turn this study into a project in order to land a scientific station in Europa that is a moon of Jupiter, and it has a layer of ice, and underneath there is a liquid layer that might have the conditions to have life nowadays. In Europa, unlike Mars, there would be life now. So the landing system will have to be very different in many aspects because we don't know much about the surface of Europa, and we know that it is very complicated and we would have to design a vessel that could also stand the radiation. And when do you think you could get there? Well, the plan we are submitting to NASA is long-term, a long-term plan. It would start in 2026. Therefore, we should start now, and the landing would be in 2033. So it's gonna take a long time. Yes, that's a lot to do. Thank you, Miguel.